So for the exercise that I wanted to work here, this is actually sort of by analogy. If you remember back when we did the fundamental theorem of algebra, I first showed that there exists that every polynomial over C has one root in C. And then you can leverage that to show that you actually have as many roots as the degree of the polynomial. And so when I was putting together the lecture for this chapter, I got to the part where we showed that every operator over a finite dimensional complex vector field has at least one eigenvalue. And I was like, oh man, you can do better than that. You can show that there's a whole bunch. And so I put that in as part of the lecture and then discovered that it's actually one of the exercises. So exercise 9 in this section. So that sneaky guy, Axler, just must have known what I was all about. Anyway, so I'll present this kind of in the tone of a lecture because that's how I was thinking about it. And it has this important idea, the minimal polynomial. And this will come back in some later chapter, like in chapter 8 or something like that. So if you're around for 406, you'll see this. So the minimal polynomial of an operator on V is the unique monic polynomial. And monic is nothing fancy. It just means that the coefficient of the highest power of the variable is 1. So it has a coefficient of 1. That just simplifies some things and allows you to specify uniqueness. So the unique monic polynomial P of smallest degree such that P of t is equal to 0. Okay, and so in the proof of the result that we did before, we saw something sort of hinting towards this. So let's look at the corollary. This is problem number 9. So, and I'm going to express it as saying T has as many roots as the degree of its minimal polynomial. Okay, and so let's see. So if we go back to the proof, so this shoot, which one was it? That was the proof of 521. Then what do we have? So from the proof of 521, we know that what was it? A0V plus A1TV plus up to ANTNV, which is the same thing as AKT to the K applied to V. Then we know that it's possible to find coefficients that make this zero out because we've got n plus 1 vectors over here and we're in an n-dimensional space, so it has to be linearly dependent. Okay, so we know we can solve that equation, and then that tells us that there's definitely going to be some polynomial that has this property that when applied to t, it's the 0 operator. So And so we can find m that's minimal with this property. So let's look at the first power of t, so that such that there's a dependence relation on those first m terms that shows up there, right? So then we've got that am is going to be non-zero, and so without and we've got v tv t squared v up to tm v is independent. Okay, but if we added in one more, so t to the m plus 1 applied to v, then it would become dependent. Okay, that's the minimality of m. And without loss of generality, we can take p to be monic. So p is going to be a0 plus a1z plus a2z squared plus all the way up to m minus 1 z m minus 1 plus, and then for the top one we can just use m. So this is the meaning of monic. That top coefficient is just equal to 1 right there. And the reason we can do that is just because am is non-zero. So we can just divide by it in order to get one that is monic. Like divide the original polynomial by am, and then you'll have a monic one. Okay, so then by minimality, if q is monic and the degree of q is strictly less than the degree of p, then qt will not kill v. Okay, so in other words, there are no monic polynomials of strictly lesser degree that will kill v. Okay, so then every root of p is an eigenvalue. Since we can write p as z minus lambda j q. Well, okay, yeah. So let me. Well, yeah. We have a theorem that tells us that you can do this, right? Because indeed, p factors by the fundamental theorem of algebra into a product of z minus lambda j, where lambda j is one of its roots. Okay, and so because we can pull out one of those linear factors like this, this implies that if you apply pt to v, then that's the same thing as t minus lambda j I qt all applied to v. And we have that okay, so the rank of qt, the range of qt is not just 0. And we have that the range of qt is contained in the null space of t minus lambda j I. And so, yeah, as is shown by this relationship right here. So this is an element of the range of qt, And then by the way we've defined P, it's going to get sent to 0. And so it's in the null space of this one right here. So since we have a non-trivial null space of this operator, then we have an eigenvalue. The end.